Okay, so this is quiz 10 review. It says quiz 9, just a typo. This is quiz 10. This is all about fluids. A lot of this quiz is just kind of centered about these types of problems, honestly, with like the tubes and stuff, figuring out pressure at certain heights, and then what they really test you a lot about too is gauge pressure versus absolute pressure. So gauge pressure is just going to be like whatever pressure you calculated, and then like minus 10 to the fifth pascals or minus 1 atmosphere, right? So that's usually something that they like to test a lot, is the gauge pressure stuff. And then this was I want to say this is the only quiz that we ever had 3 problems to do. Now, granted, problem 2 is only just like one step. It wasn't too bad at all. It was just kind of like a really straightforward, no parts to it. And you just go ahead and calculate it. But yeah, this is going to be still 20 minutes. Yeah, they never changed up the timing for any of these. But yeah, so we got a flow question, we got like a tube question, and then this is like a flow/tube question as well. But this is more like input and output, making sure that there's continuity. So, all right, without further ado, we'll get started with number 1. And I actually made a small mistake here. I should have kind of colored in, I guess, this part. This is just kind of like an explanation, but it's whatever. All right. Oops. Let me kind of go back to my pencil here. All right. So number 1, fluid in a tube. It says the L-shaped tube has one open end on the left and one closed end on the right. Water with a density of 1,000 kilograms per meter cubed fills the tube as shown in the figure and is topped off by 30 centimeters of oil with a density of 700 kilograms per meter cubed at the open end of the tube. So now for part A, they're asking us what is the gauge pressure at the oil/water interface. So they're asking us to figure out pressure. We have like different heights of this, tube that are given to us. So we know that the total height pretty much of this vertical tube here on the left is going to be 100 centimeters. This closed tube here is 40 centimeters. And then like the height of the oil here is 30 centimeters, right? And then we can infer, for example, that, well, if this is 30, right, then this is going to be 70, for example, right? Just 100 minus 30 will give us 70 for this section here. And I mean by 70, I mean basically that this height right here would be 70. That's what I mean. And this is relative to making the bottom here 0 centimeters. Wouldn't it be 30? Yes, like this part, that's why I made them the amendment. So like this part right here alone would be 30 because it would be 40 plus 30 plus another 30 would give you 100. That's absolutely right. I just meant that like at this point right here would be 70. That's what I meant. Because it would just be 40 plus another 30, so like the height here would be 70. But yeah, so we have our different heights, and then we can get our pressures as well, right? So anybody know what pressure we can immediately kind of figure out just by looking at this tube, just by the structure? Yeah, atmospheric pressure. So at which point would we find the pressure to be at atmospheric, right? So oil, where exactly? Where around here? I don't know what I'm doing. The top, there we go. So like top of the oil here in contact with the atmosphere, that'll be atmospheric pressure, right? So we can say, for example, that this is like PA, right? We can say this is at the top, and this is, 10 to the 5th pascals, 1 atmosphere. I would almost always use pascals unless they give you like torrs or atmospheres or whatever, but usually it's in pascals, and everything else would be in SI units, and then maybe you can convert at the end to whatever units they require. But yeah, top here is 10 to the 5th pascals, and then they're asking for the pressure at the oil-water interface. So when they say interface, right, so it's like where they basically kind of connect, right, where they're interacting. So interface, interacting, right? So it's this point here. So we can call that like PB, for example. I tend to refer to like the bottom points. Like if I'm saying this is PA and this is PB, like B as in bottom for me. That's how I kind of go about it, just to make it easier for myself. So PB is just like your bottom point. So whatever point is lower that you're kind of deciding between. Anyway, so yeah, PA, PB. PA is known, PB is unknown. Now, how can we, get from this known value of pressure to this unknown value? What equation or relationships can we use? The long one. So we can use the hydrostatic pressure equation, right? So we can do PA plus rho GHA, and I just this is a fancy P, so I'll just call it PGHA. It's the rho. I can't really draw it out that well, but it's a fancy P. Anyway, PB plus PGHB, right? So that's our setup for the equation. And so we can kind of begin to, plug things in, right? We know that the atmospheric pressure is 10 to the 5th pascals at the top here. And then we know our density for water is 1,000. Oops, actually, my bad. It shouldn't be density of water. It should be the density of the oil, because that'll be at the top. It'll just be oil here. So it would be 700 kilograms per meter cubed, right? Multiplied by the gravitational constant here, 10 meters per second squared for the acceleration due to gravity. And then here comes our height. So the height is probably the one thing that you have to kind of make sure that you set properly. So when I say PB, right, I want this to be at the bottom. So generally, I will set that as my arbitrary 0 centimeter point, right, relative to this top point right here. So I can say this is 0 centimeters, for example. So that would mean that, well, this thing has a height of 30 centimeters, right? Then this PA would be at a height of 30 centimeters relative to this point here. So PB, the bottom, is 0. PA, the top, is 30, right? So the height of the pressure at point A is 30 centimeters relative to making the height at point B 0 centimeters. So this would mean that we would have 0.3 meters here, right? And let me kind of move this over so I can make some space. And then, wow, oops. Then we have PB, so PB is unknown. And then considering the fact that HB here, right, the height at B is 0 centimeters, that'll just cancel out this whole term, right? So that leaves us in a pretty good spot. So we can easily figure out PB, our unknown, right, just by going ahead and calculating this big left term over here, right? Yeah, go ahead. Yeah, so whenever you have any fluid or any point directly in contact with the atmosphere, like it's out in the open here, like you can see, for example, there's just like a little bit of air in this section here. Whenever that point is completely in contact with the atmosphere or with air, that pressure at that point will always be the atmospheric pressure, which is 10 to the 5th pascals or 1 atmosphere. So for this point, for example, it's not in contact with the air, so it wouldn't have an atmospheric pressure, but this point does, right? Because it's literally right above it is air. So if you ever have an open tube, the point where the fluid, whatever you have, oil, water, whatever it is, whatever point is directly in contact with the air or the atmosphere, wherever there's just open, air above it, then that point is where you have atmospheric pressure, which is 10 to the 5th pascals. Does that make sense? And I mean, the reason that we're using basically these 2 points is, first of all, they want us to figure out the pressure at this point here, which is the oil-water interface, right? So where the oil is interacting with the water, right? Because there's like a separation here. You know how oil, if you like put oil and water together, they don't mix. So this point here is like where there's kind of like a separation, kind of a buffer, right? Where they don't mix. So we're trying to figure out the pressure at this point, right? But it's unknown to us. So, I mean, the only other pressure that we can figure out pretty easily, right, just due to the fact that it's constant, is the atmospheric pressure, which is just where any fluid would have contact with the atmosphere or air. And so we can see here that this open end right here, the oil is in contact with the air. And so we can choose that as our secondary point, right? So choosing PB or PA, and you can switch them around if you want to. It doesn't matter which point you choose, as long as like you're making sure that your heights are making sense. So if I wanted to say that this is PA, for example, and this is PB. Oh, I wrote that wrong. My bad. If this was PB and this is PA, right? Well, I'd have to make sure that my heights are making sense, right? So I can say then at that point that PA is at 0 centimeters and PB is at 30, for example, right? Or, I mean, I could have kind of the opposite, where I can say like, this is 0, right? And then this would have to be like negative 30, for example, just because it's going in like the negative y direction, I'm pretty sure. But I always like to have positive answers in my calculations, so I would usually set like PB, B as in like my bottom point, right? And then PA would be like my top point. That way that PB, oftentimes the height at PB, since it's 0 and I set that as an arbitrary point, that would cancel out. And so I can easily figure out this area here, these two terms, just because I know the PA from atmospheric pressure, and then I can figure out the height here just by going from 0 centimeters to whatever height the other point is at, and that's just going to be in the positive y direction. But yeah, hopefully that kind of clears things up. But this answer right here on the left should give you the absolute pressure, right? That should give you the absolute pressure at point B. So let me kind of, I got that right, my bad, I'm sorry. Yeah, so this should give us the absolute pressure at point B. Does anybody have an answer for that by any chance? Yep, excellent. Sounds about right to me. 2,100 pascals. So that's absolute pressure. We can find gauge pressure just by simply subtracting the atmospheric pressure from it. So we can take 102,100 pascals minus 10 to the 5th pascals, right? And that'll give us P gauge, and that should equal, because 10 to the 5th is just going to be 100,000, right? So that should give us 2,100 pascals as our gauge pressure for point B. Make sense? Okay, cool. Any other questions about A or anything about the setup of the problem at all? Nope. Okay, awesome. So part B now is asking us, what is the gauge pressure at the top of the closed tube? So now they're asking for the gauge pressure here, the closed tube, right? So I know that PA has a pressure of 10 to the 5th pascals, right? That's the atmospheric. PB has an absolute pressure of 101,200 pascals, right? Now, let's call this like PC, for example, right? This is unknown. So what do you notice about like this pressure right here? Or what relationship can we determine between like two different pressures other than like this relationship? So we know like at certain heights, right, we can use this equation to figure out pressures at two different points. But we also know another relationship, right? So awesome. Excellent work, Christian. So they're equal at horizontal distances, right? So the left side here, right side here, as long as they're like on a horizontal kind of plane or on an x-axis, right? And they're at the same height, these 2 points would have the same pressure. My bad, 102,100 pascals. Thank you for correcting my mistake there. So pressure at C is equal to pressure here as well, right? So we can say like pressure at C would be equal to pressure at D, for example. We can call these 2 different points, but in reality, they actually have the same pressure. And they have the same height, actually, because if you then go ahead and kind of look at this, right? Kind of depends on what you set your value at for your height. But if we were to set, this part right here is 0 centimeters, then this would be what? 40 plus 30, so that would be 70. So yeah, it's going to be similar thing, but different height than problem 1. Yep. And then at the end, obviously, if we use this equation, we can relate PB to PD, right? And then just by that rule that Christian mentioned, right, then we know that PD is going to be equal to PC because they're along the same height. So this will just be pretty much the same setup. You know what? Matter of fact, there. And I'll just no, well, I can't do that then. PB, there we go. That works. And then, what do we have? PB and PD. Yeah. So, PB plus PGHB is equal to PD plus PGHD, right? So, pressure at B and the pressure at D, and then we can relate that to the pressure at C, because we'll know that PD is equal to PC. But at the moment, PD is unknown, right? So we can kind of substitute some values here. Oops, I'll just take this out, and then take this out. There. Dang it. Alrighty. So PB we know is 2,100 pascals, right? And then we know that the density that we're going to be looking at here is just going to be the density of water, right? So this should be 1,000 kilograms per meter cubed, right? And then what we can do is oh man, I should have moved this further down or something. Okay, whatever. Jeez. All right, this is PD. Let's call that PD, right? So we said before that we're gonna set now PD as 0 centimeters and PB as 70, or my bad, 30 again. Right? So we can set this point as our arbitrary 0 value, right? So that way this term over here, the HD, will cancel out. So then we can get PD alone. So that would mean that our height would actually continue to be 0.3 meters. Right, because we're choosing this as our 0 value. And then this height right here is 30 centimeters. So if we do that, we should be able to just calculate this left term out and get our pressure at D, right? Yep, so 105,100 pascals, right? And once again, since we're using this pressure right here, which is the absolute pressure, we're going to be figuring out the absolute pressure of point D. So we know that this is also equal to PC, right? Based on the fact that they're at the same height. Well, if now PC is the pressure at the top of the closed tube, this is the absolute pressure, right? So what do we need to do to convert it to gauge pressure? So we know that PC is equal to 105,100 pascals. How can we convert it to gauge pressure? Yep, excellent. Minus 10 to the fifth pascals, so minus 100,000. And that should just give us 5,100 pascals for the gauge pressure at the closed tube. Does that make sense for problem 1 there? Who has a question? Kate, you have a question? Go ahead. Yeah, so the pressure at B, we actually got that from part A here. So I saw that you had joined a little late, but basically to kind of sum up what we did for part A is that we had point A and point B right here. We needed to figure out point B, which is the like interface or like the interacting surface between oil and the water. So we need to figure out the pressure right here. We know the pressure at this point is the atmospheric pressure because it's literally in contact with the air. There's like this little buffer region right here where there's contact with the air. So any point that's directly in contact with the air will have atmospheric pressure. So we said that our 2 points are going to be PA and PB, right? And we had set PB at a height of 0 and PA at a height of 30 centimeters, right? So then we use the hydrostatic pressure equation, PA plus PGHA is equal to PB plus PGHB, right? We know that the atmospheric pressure PA right here, 10 to the fifth pascals, and then we can plug in these values here, right? We had the density of oil times acceleration due to gravity, and then this height right here is 0.30 meters, which is 30 centimeters, and that's relative to making point B at 0 centimeters, right? So we set point B right here at 0, this point A is 30 centimeters, right? So then when we do that, right, this term right here, the HB, that'll be 0 because we made the height at B 0 centimeters, right? So then this whole thing cancels and we can solve for pressure at B. So once we have the pressure at B, right, that's what we're going to be using to calculate the pressure at this closed tube. So we know that the pressures at the same height that are kind of like horizontally like away from each other, right? They're on the same like horizontal plane. They would have the same pressure. So the pressure here is equal to the pressure there. Pressure here is equal to the pressure here. Pressure here is equal to pressure there, right? So if they're the same height, just kind of like drawing a line horizontally across, they should all have the same pressure. So here, here, here would have the same pressure, right? So that means that the pressure here is equal to the pressure there. All right, well, then we can kind of set these two other points. We can say PC, P closed, right? PC is equal to PD, right? Well, we can just use this equation again, right? We don't know PD. We do know PB. So we can just say PB plus PGHB is equal to PD plus PGHD, right? And we can set our height at D, this point D right here, as 0, and the height at B as 30, right? Because this height would be 30 right here. And we can figure that out because this is 100, this is 30, this part is 40, so 30 plus 40 is 70. This part would be 30 right here left over, right? So our height at point B is another 0.30 meters or 30 centimeters, right? And then the height at D, since we set it at 0, this whole term here would cancel out. So we're just left with PD is equal to the pressure at B plus PGHB. So once we calculate that out, that'll give us the absolute pressure, right, at point D, which we know, since it's the same height as point C, will be equal to PC. So PD is equal to this pressure is equal to PC. In order to figure out the gauge pressure, you just take whatever pressure you had and subtract 10 to the 5th pascals, which is the atmospheric pressure. So you always take your absolute pressure minus the atmospheric to get your gauge pressure. Yep, no problem. Hopefully that kind of made sense and it was a good wrap up for anyone who had missed anything before as well. Yeah. Any other questions about problem 1? Nope. Well, if anything comes up, just let me know and we can go over it again. But we can probably move on to problem 2. This is flow. It says fluid flows through a pipe as shown at the right. The radius in the narrow region is 1/3 RA is equal to RB. Okay. What is the ratio between the speeds at the 2 points, VB over VA? So we have RB is equal to 1/3 RA, right? And then we're trying to figure out the ratio of the speeds, essentially, right? So when you have fluid flow, what's the relationship that we know with regards to fluid? So we have this wider region right here, and we have this smaller region right here. The flow has to be what across those two different regions? Yep, Q in has to equal Q out. Excellent, right? And as an extension of that, we know that the Q, which is the flow, right, is equal to the area times the speed for each section, right? So the Q in here, Q out there, they should equal each other, right? Area times the speed here should equal the area times the speed there, right? So we can already see that we can kind of solve essentially, right, for our VB versus VA. And let me actually, instead of using 1 and 2, I'll say A, VA, AB, VB, right? So it'll help us to kind of visualize that easier. So we know that this is a pipe, right? So the area that we're looking for is not like surface area. It's actually just going to be like the cross-sectional area. So just imagine like just a circle, right? So we're just looking for the cross-sectional area. So what would the cross-sectional area that of a pipe be, right? It would just be a circle. So what's the area of a circle? Yep. So we have pi r squared, right? And this is pi RA squared, right? And we know that we have 1/3 RA, but that's going to be relevant for B, right? So we have pi RA squared times VA, and then for the area of B, right, we can kind of write that in terms of A, right? Because we have pi RB squared, but we know that RB is equal to 1/3 RA. So you can say 1/3 RA squared, right, and times VB. So this is just kind of a really, really simple ratio problem. In fact, it's only worth 2 points actually, so it's not too bad. But this is one of those questions that you can easily kind of lose points on, just because if you forget like the square for your area, for your radius, I mean, or like, I guess if you did everything right, but you forgot to like square this 1/3, for example, right? So if we simplify this out, we have pi RA squared VA is equal to pi times 1/9 RA squared times VB, right? So we can see that pi will cancel with pi, RA squared will cancel out with RA squared, so we should be left with VA is equal to 1/9 VB, right? So we can multiply the 9 over and say that 9 VA is equal to VB. And then finally, VB over VA is equal to 9. So that gives us the ratio there. So this should be like an easy 2 points to collect, hopefully. Granted that you know that like the continuity equation, and you know that the flow has to be constant, right? So the flow going in has to equal the flow going out. And you can kind of relate that to the area and the speed, plug in your points, and then make sure to realize that we're always dealing with cross-sectional areas. So if they say like, instead of pipe, if they threw in like cylinder, right? Well, don't take the area, like the surface area of a cylinder, right? Don't do that. Just take the surface area of like the cross-sectional area. So if this thing was a cylinder, right, which it is, I wouldn't take the area, like the surface area of the whole thing. I just take like this circle right here, which is just the, that's what the fluid is flowing through, right? They're just flowing through like a circle shape, right? So just take the cross-sectional area, and that's what you set up here, which is pi r squared, which is just a circle. Hopefully that made sense for part 2. I think it's pretty clear, hopefully. Any questions about problem 2 at all? Yep, the pi and the RA squared will cancel, because you'll definitely have pi RA squared here, but you'll have like for RB at least. So this should have been like pi RB squared, but we throw in, instead of RB, we can substitute 1/3 RA. So like this whole thing should have been like RB, right? So when we do that, we take 1/3 squared and we take RA squared. So that gives us 1/9 RA squared. So we can see here that the pi will cancel out, the RA squared will cancel out, and then we're left with VA is equal to 1/9 VB. Yeah, and then we can kind of solve for VB over VA. Man, I cannot clear my throat for the life of me today. Yeah, exactly. I'm like thirsty, and so yeah. If I sound raspy on the recording, please forgive me. Jeez, okay. All right, I do sound raspy. Dang it. All right. Anyway, hopefully that kind of made sense for problem 2. No, I can't go get a drink, unfortunately. I have to wait a couple more minutes here. But I'm fine. It's just like I don't know, I get raspy. So anyway, we can probably move on to problem 3 if there aren't any other questions about problem 2. And if there are, we can go over those later if you guys want. But problem 3, flowing oil. So we have oil flowing through a pipe. Density of the oil is 600 kilograms per meter cubed. Only a section of the pipe is shown. The right and the left ends are not open to the atmosphere. All right. So they're asking for part A here. They're saying that gauge pressure at the left end of the segment is 225 kilopascals, right? What is the absolute pressure at the left end? Well, they said gauge is equal to 225 kilopascals, right? Well, if I think about it, we had already kind of just established the relationship between gauge and absolute pressure, right? So what's the relationship between absolute and gauge pressure? How can we go from absolute to gauge or gauge to absolute? So, yeah, to go from absolute to gauge, we add, or we subtract, 1 atmosphere. But then to go from gauge to absolute, we can add that atmosphere back, right? Or those 10 to 5 pascals. So if we know that P gauge is equal to P absolute minus 10 to the 5th pascals, or minus the atmospheric pressure, well, if this is 225, and I'll say 1,000 pascals, right, is equal to P absolute minus 10 to the 5th pascals, right, then I can just simply add over the 10 to the 5th pascals, and I can get 325,000 pascals, right, because 10 to the 5th is just 100,000. So if you just add 100,000 over here, 100,000 plus 225,000 should give you 325,000 pascals. So that should be your absolute pressure at the left end. That's a pretty quick and easy part right there, 2 points, as long as you understand the definition or how to distinguish between like P gauge and P absolute. That should be easy money right there. Make sense for part A? Yep, okay. Now, part B is asking us to figure out the absolute pressure at the right end of the segment. So we're trying to figure out, say, like, oops, I was going to say P right, basically. Right, and this is PL, for example, P left and P right. So we're trying to figure out PR, that's unknown, right? But we know that the PL has an absolute pressure, for example, of 325,000 pascals, right? So we have this information. We can figure out this information. But we also notice something else. What's different about the left and right sides? There's height added. Yep, absolutely. Anything else? It's angled. Anything else? Cross-sectional area, right? Diameter, cross-sectional area. So this part right here is wider than this part, right? So we have a change in the cross-sectional area. Does that mean then we have a change in the flow, or would the flow remain constant? Yeah, exactly. Flow is always constant. So the change in the cross-sectional area is compensated, or we can compensate for that change by changing the speed. See, 3 and 4 meters per second. So we know that Q in, as we said for problem 2, has to equal Q out, right? So AL VL has to equal AR VR, right? Well, if AL is different than AR, right, then VL has to be different than VR in order for these two sides to be equal, right? So it's like saying, well, it's like that other problem that I did for the homework session. So if I said like 4 times 3 is equal to 12, right? Well, if this cross-sectional area is 4, this got smaller. So let's say like this is equal to 2 now. Well, in order for this side to also equal 12, well, then I have to increase my speed. So I have to say 2 times 6, right? So I go from 3 meters per second to 6 meters per second, right? Just like they said, 3 meters per second to 4 meters per second. So when you get to a smaller, more constricted cross-sectional area, you're going to increase in your speed, right? So that's a second thing that we have to account for, is the change in speed, right? So we have, not only do we have a change in height, right, that's gonna cause a change in pressure, but we also have a change in speed because we want to maintain the flow, and that's due to the basically change in the cross-sectional area. So given that, what equation or relationship should we use then? Yeah. So, as other people would call it as well, and what I like to call it too, is just the big equation with the speed. So, we have PA plus rho GHA plus half P VA squared, yeah. So PB plus PGHB plus half PVB squared. And I might as well, just because to be honest, I just wrote it down, so I'm not feeling like going back and rewriting it, but I'll say the left side is A and the right side is B, for example. Right? But yeah. So we have the pressure at A. We know that's 325,000 pascals. That's the absolute pressure, so we can kind of substitute that in, right? And then we have the height at A. We can actually set that to be 0, right? So we can say PB, this point right here, has a height of 10 meters, right? So we can set A as our arbitrary 0 meter point, right? So if that's the case, this height at A cancels out, this whole term becomes 0. So then we're just left with 1/2 times the density of oil, which was 600 kilograms per meter cubed, right? Times our VA squared, which is 3 meters per second. And then PB is unknown. We can just do 600 kilograms per meter cubed, the density of the oil again, times the acceleration due to gravity, and then the height, which was 10 meters, and then plus 1/2 times the density again, and then times our speed for point B. And let me kind of move this over a little bit so it's not as far off. But yeah. Yeah, go ahead. Oh, I see what you mean. So like, why did I throw this out? Is that what you're asking? Like, why did I throw out this term? Why did I not include it? Oh, I think she's reconnecting. No worries, no worries. But you were asking basically like why I threw this term out, essentially, right? Like why I didn't use it. Okay. So the reason is I have PA here, PB there, right? I set my point A right here to be 0 meters, and then this top point right here, PB, to be 10 meters, right? So I want this 0 meters, height 10 meters, right? So if I set point A at 0 meters for the height, this height A will turn out to be 0 meters. So when you multiply by the rest, it doesn't matter because this whole thing will just be 0. That's why I just kind of threw it out, so I skipped it because it'll just turn out to be 0. Does that make sense? Mm-hmm. So let me kind of think here a little bit. So, I mean, what you could do alternatively is just, I mean, these are just variables. So you could just say like PA, PB, right? So PB is your 0 now. So like if we switch this around, right, this would be 0, and then this term would actually appear now. So we could do that, for example. Now, if we thought about this as PA being 10 and PB being 0, well, let me kind of look at this real quick just to make sure that that could check out. So if PB was 0 and PA was 10, so this would essentially be like, so I think actually, like, if you wanted to do that, right, all you would have to do essentially is just subtract this term over, because then you would have a PGH term right over here, and you wouldn't have a PGH term over there. But the thing is, once you subtract it, right, it's kind of what I was saying before, is like if you were to, it's kind of based on like y directions, negative and positive y directions. So if I set this as 0 meters, I'd have to set this as -10. So I would have to include a negative height, I'm pretty sure, in my signs, to make sure that I'm like properly calculating this. Because otherwise, like 10 meters, I guess that would just mean like if you said this was 0 and this was 10, well, in actuality, that would mean like 0's here, 10 is actually up here further. So like, I don't know. Yeah. But I think you would have to make your height -10 meters then. Because think about it, like density is going to be the same, gravity is going to be the same, and the heights, if we said this is 10 or this is 10, it doesn't matter, right? But if we were to say then that PB is at 0 and PA is at 10, right? If we were to say that, then we'd be looking at this being 0 and this having HA be 10, basically, right? So that would mean that I could essentially kind of, without having to calculate the whole thing over again, what I could do is I can just subtract this term over, right? So then I'd have 0 for this term, like this term wouldn't appear on the right, but some PGH term would be on the left, right? So if I, basically what I'm saying is like you would end up with 325,000 pascals plus half times 600 times 3 squared, right? And then minus 600 times 10 times 10, right? This would equal PB plus 1/2 PVB squared, right? So it's like, you see that if I were to cancel this out, right, when I said that PA is equal to 0 and PB was 10, right? Well, if I switch it around, you can see that, okay, well, PB is 0 now, and PA is 10, but look, there's a negative sign. And so that negative sign is basically showing us that height has to be -10, basically. Does that make sense? So you have to make sure that it kind of aligns with like your coordinates. Making sure that if you go downwards it's -10, upwards it's +10. Yeah, you can. Yep, definitely, that's absolutely right. So you can use the hydrostatic equation when your fluid is static, so not moving at all. If the fluid is moving, you can use Bernoulli's equation. Right? So as soon as you throw in any type of motion where we have like speed and stuff like that, then you use Bernoulli's equation. But as long as the fluid is static, is not moving, then you use hydrostatic normally. Yeah, and I mean, if we were to throw out all these values, right? If we just had like this orientation here, you can absolutely just use the hydrostatic equation. Yeah, Caroline's absolutely right. Awesome. But did that make sense about like the whole height thing? I just want to make sure that like the height stuff kind of made sense. Yeah, I mean, I would just prefer, like, if I'm doing these problems, like I would just prefer to have my bottom point be 0 and my top point be a positive number. Because otherwise, like, you'll deal with negative signs, and I don't like that. So, so we use the hydrostatic equation when the fluid is static, so it's not moving, right? There's no motion to the fluid at all, and use Bernoulli's equation when there is motion, right? Because then you throw in like the change in and the speed and stuff. Because think about it, like, technically this equation will work for all of them, right? But if the fluid is static, right, then that just means that there's going to be like, I guess this is a bad way of saying it, but let's say that for your continuity equation, right, if your velocity stay the same or like your speed stays the same on either side, well, VA would equal VB, right? And assuming the densities are the same, obviously, then these terms would cancel out. So then you're just left with the normal hydrostatic equation. Yeah, hydrostatic is the one without the speeds. So that's why Caroline was absolutely right with the whole idea that if it's static, right, if it's not moving technically, if there's no like net motion per se, then or if there's no acceleration, let's say, so no net force basically, so no acceleration, then in that case, we can just use the hydrostatic equation, because at that point, then if it's not accelerating, so if it goes from 3 to 3, well, VA is going to equal VB, so you can just subtract these two terms because they'll cancel out, right? Because the density is the same on either side, so if the velocity is the same as well, or the speed is the same, then these terms will cancel out, and you're just left with PA plus PGHA is equal to PB plus PGHB, right? Otherwise, if there's some kind of net force, right, if there's the acceleration, if the speed increases, right, then we're going to be using Bernoulli's equation, because we'd have to factor in the change in the speed. But yeah, and then hopefully this height stuff made sense. Yeah, like I said, I would just prefer that you set your bottom point at 0 and your top point at some height, like we did here, where we said this is 0, for example, this part was 30. We said this part was 0, this part was 30. So just make your bottom point your arbitrary 0 point, right? So yeah. And you can just imagine it as well, like kind of drawing a coordinate system. So if we said this is the origin, right? This is the positive y-axis, this is the negative y-axis, right? Positive y, negative y, right? If I set it here, this becomes positive y, this becomes negative y, right? Like that. So I just want to set my bottom point always to be the origin and my top point to be in the positive y direction, so I can easily just calculate the height and all my answers to be positive. But yeah. Anyway, if you go and like simplify all these terms, you subtract everything over, right, and you calculate for PB, you should get 262, I think 262,900 pascals. Yep. And that's the absolute pressure. Now, if they wanted the gauge pressure, it's just a matter of subtracting the atmospheric pressure, which is minus 10 to the 5th pascals. So that would just be minus 100,000. So that would leave you at 162,900 pascals. And guess what? That's part C. So I didn't look at part C. So there, I gave the answer for it already. Darn. Yeah, so for gauge pressure, you take the absolute minus 10 to the 5th to get your gauge. So P gauge is equal to P absolute minus 10 to the 5th. And then P absolute is equal to P gauge plus 10 to the 5th, right? So just adding over 10 to the 5th. And these are two really important equations to know. I mean, they're not on the equation sheet, so I wouldn't call them really like equations per se, nor were they like stated as a definite equation in the slides, but basically it's a relationship that you should be aware of, that to get your gauge pressure you take your absolute minus 10 to the fifth, and to get your absolute you take your gauge pressure plus 10 to the fifth. And so yeah, 162,900 for the right pressure gauge, right? Because if we want to figure out P gauge, we take P absolute on the right minus 10 to the fifth, right? So that's 262,900 pascals minus 10 to the fifth, and that should give us 162,900 pascals, right? Is it on the equation sheet? I haven't looked at the equation sheet, to be honest, but oh, awesome, it is. Cool. So P gauge is equal to P absolute minus 1 atmosphere, and 1 atmosphere is 10 to the fifth pascals. Cool. Well, there you go. And yes, oops, I forgot. Yeah, so they do want it in kilopascals, so we divide by 1,000. So this should be 162.9 kilopascals. Yeah, 160.9 kilopascals. But yeah, that's problem 3. I'd have to say, like, I mean, the equations are long, I won't deny that. But in my opinion, just because I think the professors are a little bit aware of like the fact that this fluid stuff is a little confusing at first, I personally felt that this was one of the easier quizzes that we've done. So I don't know, do you guys agree with that? Like, I feel like this was a lot of like plug and chug. It was, I mean, once you figured out like what points you wanted to use and stuff, like it was a cakewalk. Do you guys agree? Or maybe I'm just biased, I don't know. At least I hope I made it at least easier to kind of like follow along with all this stuff. Yeah, the online homework for the fluid stuff, it's not that great, to be honest. Because I felt like they threw, like, I'm pretty sure they threw in like a bunch of like science applications to it as well, and that might make things confusing. But I felt like the written homework from here on out for the rest of the semester does a much better job. I feel like after a while, like the online homework just became unnecessary. But yeah, any questions about any of these problems? Or I mean, we could kind of like spend, I guess, the last 20 minutes or so, kind of going over important topics, I guess, from the slides. Or if you guys have any questions, just in general that you want to go over. No, that was problem 3. It's just that problem 2 was so small that it seemed like a part of problem 3. But yeah, 1, 2, 3. Yeah, no problem, Caroline. I'm really glad to hear that. And thank you for coming to pretty much like all my sessions, I guess. Or maybe I'm just blind. I don't know. But I feel like you guys are doing a great job at coming to these sessions, and I'm very grateful for that. So I have to say I look forward to these sessions every week. So yeah, absolutely. I certainly hope that you don't have something harder, because it's like there's only so much that you can ask with all this stuff. But definitely know Bernoulli's equation, and make sure that you're like aware that, okay, if there's a change in cross-sectional area and there's a change in like the speed and stuff, I got to make sure to factor in that change, and the only way you can factor in that change is to use Bernoulli's equation. Um, blood vessels. If you do get blood vessels, it's just that I could foresee being like a flow equation type thing. So it'll be really similar to this, like a blocked artery or something like that, right? So in that case, we can kind of move over to the lecture stuff. So kind of going over that idea here with Bernoulli's equation and the principle. So like imagine like this is your artery, right? You have consistent flow through here, right? Let's say this is, I mean, it kind of constricts or there's like a blockage or something, so the flow isn't as, I guess, there isn't much, like a lot of space for the blood to flow, for example, right? So according to the Bernoulli effect, right, you have pressure is actually higher where the fluid is moving slower, right? So this is a little weird because you can see here that the velocity here is smaller than or the speed here is smaller than this constricted area, right? So you can see that like the vector here is small, this vector here is larger, right? So the speed here is smaller, speed here is greater, right? But they're saying that when the speed is smaller, we're at a point where the pressure is higher, right? So that's a little confusing because you would think that pressure would increase if you constrict it a little bit, right? But I guess the way to kind of think about this whole pressure and speed thing is that basically at this point where I have like more room to operate, right? I'm going to want to increase the pressure, right? If I increase the pressure, or they say pressure is higher, right? If I increase the pressure, I'm increasing the force. Force is equal to mass times acceleration, right? So if I'm giving this part right here a force, I'm giving it an acceleration, right? If I'm accelerating, there we go. If I'm accelerating, I'm actually increasing my speed. So I go from a slower speed to a faster speed, right? If I'm applying some kind of acceleration. So that's why they say the pressure is higher at a point where you're moving slower. And that's why usually your pressure is higher at like those larger cross-sectional areas. Because if you remember, here you could see that VB, right, the velocity here is much greater than the velocity here, right? And if we think about it too, we can look at this problem and recognize that, well, we had an absolute pressure of 325,000 here, but only 262,000 there, right? So that's kind of weird, right? Because you assume like, okay, if I compress something, right, if I press down on something, if I make this cross-sectional area smaller, if I squeeze it, it's going to have a greater pressure. Like that's like the intuition you would think of, right? But it's actually the opposite because I want to increase pressure here, right? I want to have a higher pressure here to ensure that if I have a higher pressure, right, I increase my force, giving an acceleration, right? And if I accelerate, my speed gets faster, right? Or if I increase in my speed. Yeah, so for this chapter especially, do not trust your instincts. Like, whatever you think is right, wrong. I'm sorry, but like 9 times out of 10, whatever you assume or you think is right is just probably going to be wrong. So I would most likely always refer back to an equation or a relationship that you for sure know or are aware of from the slides or whatever you learned. But yeah, I mean, everything before this point, you could use your intuition, but like now it's just like your instincts are not there. You can't use them because they will trip you up. And so it would make sense then that the pressure here is lower, right? Because you're already traveling at a higher speed. So I want to, apply some higher pressure in this wider area to like push the liquid or the fluid through faster, right? So if I kind of relate this to like a vessel or something, right? So if I have a clogged artery, my heart is going to want to work a lot harder to push blood through this constricted vessel, right? Or this blocked artery or whatever. So I'd have to increase pressure where it's not constricted, basically. So I'd have to increase the pressure here to ensure that this blood flowing through this constricted area or this blocked area is able to get through with the same like flow, or at least I try to, right? Because I know I have to have Q in is equal to Q out, right? Well, if it's blocked, you would think that you're going to get less blood flow through here, right? Because it's blocked, right? If I have like a lot of plaque or something, the flow is going to be blocked. But in order to maintain or make sure that the flow is the same, right? To ensure that Q in is equal to Q out, right? I'd have to increase speed. Because remember, A1V1 is equal to A2V2, right? So if my area for A2 got smaller, right, because it got constricted, then my speed for V2 has to get greater, right? So it's a relationship that I was talking about before. So if I had 3 times 4, right, my area for 1 is 3. If it got constricted all of a sudden and became 2, then I have to up my speed. My speed has to increase in order to ensure the same blood flow. So your blood has to flow like a lot faster through that clogged artery or that clogged section in order to maintain that or in order to ensure that the blood flow is the same, right? So hopefully that kind of makes sense from like a biological standpoint to kind of relate the two. But to even ensure that the speed is increasing, I have to make sure that wherever my arteries aren't clogged, I apply a higher pressure, right, where it's slower, to make sure that where the fluid, the area or the areas that are constricted, it's moving faster, right? So higher pressure where it's moving slower, lower pressure where it's moving faster. Does that make sense? Okay, cool. But that's probably one of the most, like, I'd say difficult kind of things to wrap your head around, especially, and that was probably the hardest for me. Just because, like, you have to make sure and keep, like, in the back of your head that your flow has to be the same in and out. And so if there's a change in area or whatever, you have to make sure that there's a equivalent change in your speed to make sure that the flow in and out has to be the same. And so it's like how I said, like, you have to make sure that the areas that aren't constricted, you push harder there, right, to make sure that the blood flows at an adequate amount in the constricted area. So your heart kind of has to work harder while it can, right? Because once it hits this part, this clogged area, this constricted area, it can only do so much, right? So when I have freedom to move here, I want to make sure I'm applying a greater pressure, greater force, thus acceleration, to make sure when I get here where it's clogged or where it's constricted, that I'm increasing my speed to a point where the flow in and out has to be the same. But yeah. Other than that, I want to say, like, the lift stuff, don't worry about that. We'll eventually get to, like, lift in later chapters, but they always manage to include it in the slides and make it seem like it's a huge deal now. It really isn't at the moment. But some of these example problems are good as well to go over. These are some conceptual problems we can kind of go over here as well. So if we said this rule that Christian mentioned earlier in the session, so we have pressures at point 1 and 2. Since they're at the same height, right, horizontally from each other, they would be at the same pressure, right? Here and here are the same, here and here are the same, right? But if I said point 1 and point 2, those wouldn't be the same pressures. So they have to be the same height horizontally from each other. We can say 1, 2, and 3, for example, right? So we have 2 and 3, we know those would be the same. But 1, right, is going to be less than 2 and 3, right? Why? Because we know that as you increase in height, or increase in depth, right? If I go deeper and deeper and deeper, right, then the pressure would increase, right? Because there's, if you imagine like the Earth, right? If I, go scuba diving or something, pressure is going to keep increasing as I go deeper in the ocean, right? Because then you have not only the water above you pressing down on you, but obviously you have gravity, and then you have like all the layers of the Earth like the atmospheric layers, I mean, right? Pressing down on you. So the deeper you get, the greater the pressure. This is kind of like the flow stuff again. So if I have flowing in 10, 1, and 2, right? 10 plus 1 plus 2, right? That's 13. If I have flowing out 8 and 4, well then, what would be my flow out here, right? Because I know Q in has to equal Q out, right? So if I have 13 flowing in and 12 flowing out here, then what does the flow have to be here? 1, right? Because then 8 plus 4 plus 12, or plus 1 would be 13. So it's like saying flow in is positive, flow out is negative. So positive 10 plus positive 1 plus positive 2 is positive 13. Negative 8 minus 4 minus 1 is negative 13, right? So I have to make sure that the flow in is equal to the flow out. So yeah, flow rate is constant. Based on the continuity equation, what comes in must come out. So we have 13 milliliters per second coming in. So we have to have 13 milliliters per second going out. So 8 plus 4 plus 1. Right? And then the rest of these I want to say are just like, yeah. They're either similar problems as we did to the quiz, right? Or actually, yeah, they're pretty much the same, right? This will just be like a curved tube instead of like the other tube that was more like rectangle shaped, I guess. But I don't know. I don't want to spend too much time like going over the same types of problems. I want to make sure that we kind of hit on like concepts, because I can always, I'm going to share like this slideshow document with my work and stuff. But as usual, like I want to make sure that like you guys know, like I might have made a mistake here or there, so I wouldn't take these like 100%, you know, correct, just because like, I don't know, when I'm writing, I could, you know, write a value down incorrectly, or I might skip a step or something, and so it might be hard to follow a little bit. But like I like to think that I have some insightful notes or something here and there, so I'll definitely share those on the drive, and hopefully those will help. But going back here, there was, let me see this problem. So gas flows from left to right through this pipe whose interior is hidden. At which point does the pipe have the smallest inner diameter? Okay. Yeah. So if we have flow from left to right, point does the pipe have this? So B, pressure is the smallest. Okay, so looking at these pressures first, right? So pressure here from point C is the greatest because it's pushing down with like, you know, it's pushing that liquid down the most. So it has the greatest pressures. So this is more like, okay, this is more like a qualitative thing. So just looking at like how much at each point is pushing like the liquid down, right? It says gas is flowing from left to right. So if that gas pressure is greater than the liquid pressure, it's going to be pushing it down more, right? So we can see that the pressure at C is greater than the pressure at B and greater than A, right? And so if we were to order these, we'd say C is greater than A and A is greater than B, right? Because this pushes it down a lot more. This pushes it down a little bit, and this barely pushes it down, right? So we say like PC is greater than PA is greater than PB, right? So given that, we know that the pressure is greatest at C, it's pushing down the most, right? We can kind of look at like Bernoulli's equation. This is how we would relate to it, because we're wanting to figure out what has the smallest inner diameter. So like if we said, for example, so we have PC is greater than PB, right? PC is greater than PB. So if we kind of like were to plug sample, numbers in, or we were think about it with relationships, right? Then if this was, I don't know, 10 and this was 2, for example, right? Um, I guess I want to think about this. So I want to basically we're going to relate it to speed, and from speed we can relate it to the area, and obviously from the area we can relate it to um, the diameter and stuff. So I guess if you have bigger pressure, then we have let's say maybe slower speed then. Yeah, based on Bernoulli's principle. So this is kind of going back to this part here. So highest pressure is where the fluid is moving the slowest, right? Or the gas is moving the slowest. So if this is the highest pressure at point C, this is actually moving the slowest. So we can say like VC is smaller than VA is smaller than VB, right? Because this will have the greatest pressure, this will be in between, this will be the smallest pressure. And where we have the smallest pressure, where the pressure is lower, it's where the fluid is moving faster, right? So VB is the point where the fluid is moving fastest, right? Then we know that kind of also, once again, relating here, right? So if we have a fluid moving faster, it's going to be in an area that's more constricted. So if fluid is moving faster in an area that's more constricted, well, if it's more constricted, then it has a smaller cross-sectional area, so therefore it'd have a smaller diameter. So point B. So you have to go relate it from pressure to the speed, from the speed to the area, and from the area to the diameter. Does that make sense, like the relationship jumping between all of them? Because it's all just based on Bernoulli's principle. Because like pressure is highest where you're moving slowest, right? Pressure is lowest where you're moving fastest, right? So this is my lowest pressure, it's my highest speed. So lowest pressure, highest speed, right? And also, if it's my highest speed, I know it's going to be moving in an area that's like more constricted, right? Exactly. It's kind of like it doesn't have time to push it in, so you need to like accelerate it. You're going to apply a greater pressure here, lower pressure there, right? So lowest pressure, highest speed, and then the smallest area. So low pressure, highest speed, smallest area, right? And so if your area is smallest for point B, well, we know then based on the area pi r squared, right, the radius would be smaller. And if the radius is smaller, well, the diameter is 2 times the radius. So if the radius is the smallest for point B, then your diameter would be the smallest. Does that make sense? Yep. Okay. Otherwise, let's see here. So yeah, no problem, guys. Yeah, I'm not sure. I guess if you, I mean, we can call it. Yeah, it's 7:33. Yeah, I mean, I think I touched on like the two most important things in my opinion, but other than that, oh, I'd say maybe go over this question for sure. This one right here was a pain because I had to think about it in a different way, but otherwise it really just, like, I feel like they repeated some of the same problems. So if you take some of those example problems at the end, plus like the quiz problems that we went over and the written homework problems for sure, then you should be okay. Which this one was 4 because of the height. Yep. So this was like at a lower height, right? Or it's like, so like if we said this is 0, right? This would be the deepest point. So that's why there would be a bigger pressure there, and so that would force out the cork. I thought about it like if you rotated this, right? I thought this was 0 and this is the height that we're going in. So I thought 3 was gonna pop out. That's why I was confused a little bit. But yeah, I thought, I was like, oh, well, if I'm pushing down, right, wouldn't this be the greatest pressure because it's like at the bottom? But I guess what they were looking for is that this would be your bottom. So like our height is vertical and not horizontal in that case. But yeah. Otherwise, it's really just about the hydrostatic pressure equations and the Bernoulli's equation. But yeah, I'll make sure to share these slides as well, and I'll have the whatchamacallit, the quiz review uploaded as soon as possible. But yeah. Yep, no problem. Hope you guys have a great night too.